Hello again. Today we're going to begin the first of two sections dealing with the concept of rational functions. Rational functions are related to the concept of polynomial functions, which we just got done with, in that they are the quotient of two polynomial functions. And so if you have the notes that were on Blackboard, or if you just want to keep track on a blank sheet of paper, we'll go to those papers and get started. The first problem we're going to look at are some rational functions we've already seen already. Um, these go back to when we were doing transformations of functions. There were two functions. One was called the reciprocal function, which you see on the left here. Two curves on the positive side of things. You see that as x gets bigger, the reciprocal gets smaller. Reciprocal of 1 is 1, reciprocal of 2 is a half, 3 a third, a fourth, and so on. As we approach the x-axis from the top, and as x gets become a smaller positive number, its reciprocal gets larger. Reciprocal of a half would be 2, reciprocal of a third would be 3, and so on. And we approach the y-axis as an asymptote. You're going to hear a lot about asymptotes tonight because they're quite common in rational functions. On the negative side of things, much the same, except of course the reciprocal of a negative number is a negative number. So the reciprocal of -1 is -1, -2 would be a negative half, -3 a negative third, and so on. Again, approaching that x-axis as we go out. And then as we get closer to 0, reciprocal of -1/2 is -2, reciprocal of -1/3 is -3, and as we get closer to 0, the reciprocal approaches negative infinity. And as a result, the other function we saw here is the reciprocal function squared, 1 over x squared. It's much like the reciprocal function in terms of shape, except for one difference. You'll notice that when the negative numbers have their reciprocal squared, they become positive. And so this shape, it doesn't get reflected up because the numbers are squared, but it'll have the same shape up in the second quadrant. Whereas over here, the first quadrant is a little slightly different curve, but very similar, and again in the first quadrant. So basically we're looking at this type of curves, opposite quadrants for x, 1 over x, adjacent quadrants for 1 over x squared. And we're going to be looking at some transformations of those graphs. First one we see is 3 plus 1 over x squared. If you recall, when we take a curve or a function like 1 over x squared and add a constant to it, that simply adds 3 to the y values, with the result being a shift upward 3 units. And so essentially what happens here is the x-axis moves up 3 notches, and that horizontal asymptote that we saw on this curve over here is now moved up here to y equals 3, and the graph shifts up 3 places with the two curves going again in those adjacent quadrants. The second function we have here, 1 over x minus 1 plus 1, there's actually two transformations. The first one, forget the plus 1 for a minute, 1 over x minus 1. Recall that when the x is replaced by x minus 1, we subtract 1 from the x values actually all increase by 1, and the result is a shifting of the graph not to the left, but to the right 1 place. So we're going to take this graph over here, 1 over x, and shift it 1 place to the right. Okay, so the y-axis moves over 1 to the right. Then the plus 1 does much the same thing as the plus 3 did in the previous problem. It's a vertical shift, adding 1 to all the y coordinates, shifting the x-axis, if you will, 1 place up, and along with it, every other point on the graph. So our new origin, so to speak, is going to be at the point 1, 1, as the y-axis moves over 1 and the x-axis moves up 1. And the two curves get curved in, much like they were with the graph of 1 over x up here. And finally, the third example of our tree here has actually a three-part transformation. We've got 2 minus 1 over x plus 1. So let's start with the rational expression 1 over x plus 1. Just the opposite of what we saw in the previous problem, where we had 1 over x minus 1. Remember, subtracting 1 from the x increase the x values, moving everything to the right one place. This is going to decrease the x's by 1, moving the y-axis 1 to the left. So my y-axis is now going to be 1 to the left at the vertical line, x equals -1. Second transformation comes when we multiply that fraction by -1. Recall that when an expression gets multiplied by a negative number, the result is a reflection, if you will, across the x-axis. So that's why in this graph, we see the negative side of the y-axis being flipped up into what would be the third quadrant, and the positive side of the y-axis being flipped down into the fourth quadrant. That's why you see the curve up here in the upper left and lower right. And then last but not least, after we take the opposite of 1 over x plus 1, we've got this positive 2 here. Now notice that 2 is positive. Excuse me, there it is. The 2 is positive as the minus sign goes with the fraction. And so this results in a vertical shift upward. So now my y-axis has been moved 1 to the left. My x-axis has been moved 2 upward. So the vertex is now at -1, positive 2 is right here. And the graph has been flipped because of the negative sign in front of that fraction. And that's why the curves are in these two quadrants. Okay? Anyway, a little bit of a review of transformations as well as an introduction to some of the simpler rational expressions, rational functions. Now, we're going to be moving into some other features that rational functions possess. As you can kind of see, if we look at the directions of the next problem, where we talk about domain and range and intercepts, but then the concept of asymptotes. Asymptotes, as we saw in the previous problem, are lines, normally vertical or horizontal, that the graph will approach, but not intersect, at least in many cases. Vertical lines, like the one you see on letter A here, are vertical asymptotes. They will not be crossed as they represent points where the graph is undefined. Horizontal asymptotes are asymptotes that basically the curve approaches as it heads to infinity, as it goes out to the right, to the left. It's very possible that a graph will cross a horizontal asymptote somewhere in the middle here, but as it goes to infinity, it will approach and not cross that horizontal asymptote. And then, as we'll see in the next problem here, there are things called slant asymptotes, or sometimes called oblique asymptotes, O-B-L-I-Q-U-E. And those are lines that the curve will approach, again, as they go to negative or positive infinity. And again, they might cross them in the middle, but they won't cross them as they go to infinity. They'll simply get closer and closer and closer. So let's start looking at these problems. The first thing we're asked for is the domain and the range. You recall from looking at graphs of functions earlier, we saw the domain, we thought in terms of vertical lines. And so we think in terms of vertical lines, what vertical lines would cut this graph? Well, because this curve goes out to infinity here, you see all vertical lines over here will cut the graph as we come to the right. And as we go out to the left, all vertical lines will cut the graph. There's just one vertical line that doesn't cut the graph that we kind of hopped over here in the middle, and that's our vertical asymptote. And that looks to be the line x equals -1. X equals -1 is 1 unit to the left of the y-axis, and therefore that line is not part of our domain because there are no points on the graph with an x-coordinate -1. So in our domain, you see we simply put the restricted value of -1. Every other number is fine. If you have to do it in interval notation, you would say -infinity up to -1, along with all the points from -1 out to infinity. But you'd use parentheses around the -1. It's not going to be included. The range, just like we thought of vertical lines for domain, for the range we think of horizontal lines. And in this case, horizontal lines starting at -infinity will not cross the graph. You'll see as the curve doesn't come below the x-axis. The first curve or horizontal line that's going to cut the graph is not on the x-axis, since that looks to be an asymptote, but it'll be above the x-axis. Everything y values greater than 0. And as we go up, you can see that the graph does go to infinity, and the graph will continue to cut the horizontal lines to infinity. So our range will go from 0 to positive infinity. You'll notice the 0 is not included in that case because, again, where the curve doesn't hit the x-axis. Intercepts, well, the only place the curve hits either axis is right here at the point 0, 2. That would be a y-intercept. But you'll notice it doesn't hit the x-axis. That's our horizontal asymptote. And therefore, one intercept at 0, 2. And as far as asymptotes go, well, we've spoken a lot about this vertical asymptote. So let's look at that first. The vertical asymptote here is a vertical line with the x equals, in this case, -1. That will be what the line approaches as x gets closer to -1 from the left and right. The curve will head towards infinity. And then the horizontal asymptote, well, that's our x-axis. And our x-axis, remember, has the equation y equals 0. So y equals 0, our horizontal asymptote, x equals -1, vertical asymptote. As far as letter B goes, here you see that when it comes to talking about domain, as we go out to the left, now this part of the curve is going to keep going out, keep going up, following that line as it continues upward. And therefore, our domain will start at -infinity, and it will come to the right with us all the way until we get to that y-axis again. You'll notice the curve will not cross that y-axis. As it comes at the y-axis from the left, it goes towards positive infinity. As it comes towards the y-axis from the right, it goes to negative infinity. So 0 will not be a part of our domain. But after we cross the y-axis again, we'll start crossing the graph as the curve will get closer, 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 closer to it. And as it goes out, it will continue to go outward as well. So our domain, all the numbers except, again, x equals 0. And again, you could put from -infinity to 0 and 0 to infinity, or simply put x cannot be 0. The range, well, the range is a little tricky here because you'll notice that we started -infinity and the curve does head downward. So the range does start at -infinity and it'll come up. But as it comes up, you'll notice once it hits -2, it looks like, all of a sudden, it stops crossing the graph. All the way up to this point, where y is +2. And then after that, because the curve opens upward, it will continue to cross the graph up here. So the range has two parts to it. The first, from -infinity up to a -2. And then the second, from +2 to positive infinity. And those 2 points, -2 and +2, should have brackets on them. Can't really tell from my answers, but there should be brackets. far as intercepts go, well, in this case, we don't have any intercepts. You'll notice our x-axis, the curve does not cross it. And likewise, because the y-axis is an asymptote, the curve will not cross that either. So no asymptotes, or intercepts, excuse me. Now we come to the asymptotes. Well, we already mentioned the vertical asymptote, the y-axis as being the vertical asymptote, which the curve approaches from the left and from the right. And the equation of the y-axis is just x equals 0. Now this other dotted line that we see the curve approaching, that is, as I mentioned before, called an oblique asymptote, or a slant asymptote. And so the equation for that, well, you might recall how to find equations of lines. Easiest form is slope-intercept form, and it turns out we've got what we need for slope-intercept form. You can see we're given a point on the line right here at negative 1, 1. And we also know the line goes through the origin, which not only gives us a second point, but it also gives us the y-intercept, which would be 0. So for our slope, we'll go down 1 over 1, down 1 over 1. Slope of negative 1 over 1 is simply negative 1. So we have a slope of negative 1, our y-intercept is 0. The equation would be y equals negative 1x plus 0, or simply y equals negative x. That would be the equation of our slant asymptote. And then finally, our third example here, got 3 parts to the graph. Let's start with the domain. You'll notice that the left part of the graph is out to negative infinity. So our curve, our domain, will start at negative infinity as this keeps going over. And it will continue to the right until we get to this vertical asymptote again, where the curve doesn't cross it. It goes closer and closer as it heads to positive infinity. And on the right side, it goes closer and closer as it goes to negative infinity. But it won't hit that vertical line, which would be x equals negative 1. Then, as we continue past that asymptote, you see our vertical lines will continue to again cross the graph until we get to this other dotted line, which is our other vertical asymptote. That would be at x equals a positive 1. Curve, you see, gets closer to it as it heads towards, comes that positive 1 from the left, going to positive infinity, and from the right side as it approaches positive 1, it goes negative. But again, it doesn't cross. And then once we pass 1, the curve would continue to intersect vertical lines as the curve heads out to negative infinity. So our domain is going to be actually 3 intervals from negative infinity up to negative 1, including, and then the interval from negative 1 to positive 1, again not including, and then the interval from positive 1 to infinity, again not including positive 1. Or simply put, everything, all x values not equal to positive or negative 1. Our range, the y values, well, again, you see 2 parts of the curve heading to negative infinity. So our range will start at negative infinity and come up. And even though this part over on the right stops as we get to 0, this part in the middle doesn't. So we'll continue to intersect the graph as we pass 0 and move up to positive infinity. So our range here would be all the y values from negative to positive infinity. Intercepts, well, it looks like the only place we intersect any axis is at the origin, where we intersect both axes, right here, 0, 0, being our only intercept. We don't intersect the x-axis anywhere else, and we don't seem to intersect the y-axis. And finally, the asymptotes. Well, you've got the 2 vertical asymptotes. Those 2 dotted lines are very easy to see. X equals negative 1 over here to the left of the y-axis, and x equals positive 1 over here to the right of the y-axis, along with the horizontal asymptote, which isn't so easy to see because it's not, doesn't really draw your attention with a dotted line, But that horizontal asymptote on the x-axis would be the line y equals 0. Okay? And that takes care of those problems. Now, with all the talk about asymptotes, we're going to look at some equations of rational functions and find those asymptotes. For that, I'm going to switch over here to a different document, which will tell us how to do that. First thing we do when we have a rational function is factor the numerator and denominator and see if there are any common factors, like x plus 3 in this case. If there are, we're going to cancel those common factors and deal with the simpler function. The 2x, in this case, would be 2x minus 1 over x times x minus 3, with the x plus 3's canceling out. Those x plus 3's are going to be what we'll call holes in the graph. And we'll talk about those a little bit more in our next class. But they're not asymptotes. Now, when it comes to asymptotes, vertical asymptotes are kind of easy to spot, at least if you're good at factoring, because vertical asymptotes represent a place where the function is undefined. And you recall, since the function is a quotient, it'll be undefined when the denominator is 0. And so, again, once you've factored and simplified a rational function to find the vertical asymptotes, what you'll do is set the denominator equal to 0. In this case, the denominator is x times x minus 3. And of course, when the product is 0, it means one of the factors is 0. So you set x equal to 0, and you set x minus 3 equal to 0. And you have two solutions. X is 0 or x is 3. And those would be your two vertical asymptotes. Your two vertical lines, x equals 0 would be the y-axis, and x equals 3 would be the vertical line that's 3 units to the right of the y-axis. Now, what about those horizontal and oblique asymptotes? Those are going to be a little trickier. The key is the degrees of the numerator and the denominator. Degree being the highest power of the numerator and the highest power in the denominator. Now, the first example we see here, we see the numerator has the highest power of 1, that's x to the first plus 2, and the denominator x to the second minus 4. So the denominator has a higher power than the numerator. When that's the case, as you'll see over here, the largest exponent on the bottom is greater than the degree on the top. The horizontal asymptote is simply y equals 0. And that's your x-axis, okay? And that's the case here. The x-axis would be your horizontal asymptote, okay? Now, when the numerator has a higher power, as is the case here, and we've got y equals x to the fifth plus 2 over x minus 4, in that case, there is no horizontal asymptote, okay? Because the numerator is just going to grow much faster than the denominator. So it won't approach a limit. It'll just get bigger and bigger and bigger, or smaller and smaller and smaller. So no horizontal asymptote in that case. If the two have the same degree, as is the case here, we've got 2x cubed plus 2 and 3x cubed minus 4. In a case like that, what we're going to have is, what we'll do is put, well, basically as x goes to infinity, everything, the 2 and the 4 become insignificant. And we'll have 3x cubed over 2x cubed. And when the x cubes cancel, all we're left with is 2/3. Okay? As it says over here, the degree is the same on top and the bottom. Divide the coefficients of the variables with the highest degree on top and bottom. So in this case, we're just going to divide the coefficients 2 over 3. and we'll get y equals 2/3 as our horizontal asymptote. Okay, so bottom's bigger, x-axis, y equals 0. Top's bigger, no horizontal asymptote. If they're the same, just take the coefficients of the two highest power terms. Put 2x cubed over 3x cubed, cancel the x's, and you get y equals 2/3. Okay? What about those slant asymptotes? Well, the slant asymptotes are kind of a corollary to up here when we said there was no horizontal asymptote when the numerator had a bigger power. That's true. There is no horizontal asymptote. However, if, as it says over here, the degree on top is 1 more than the degree on the bottom, in other words, it's bigger by 1, then you're going to have a slant or an oblique asymptote. Okay? And to find the equation of that line, that slanted line, like we saw on the other when we were doing some of those problems, what we're going to do is use long division to divide the polynomial on top by the polynomial on the bottom. And here you see that long division, dividing 2x squared plus x plus 1 by x minus 4. Okay, now technically, we could have done this one because we were dividing by x minus 4 synthetically, if you prefer that, but you won't always be able to use synthetic division because the denominator might be something like x squared plus x minus 3 or something like that. So good to be, again, familiar with that long division problem. What we're going to do is, once we get to the remainder, we're going to just ignore the remainder and look at the quotient. And that quotient will give us the equation of our slant asymptote, our slanted line that the curve will approach. In this case, it will be y equals 2x plus 9. Okay? Anyway, well, we'll be coming back to those quite a bit as we go back to our paper and look at the finished problem at the top. First thing we're asked for is a vertical asymptote. Vertical asymptote when the denominator is 0. Well, the denominator is x minus 6. We set it equal to 0. We get x equals 6. Okay? Horizontal asymptote. That's when we look at the degree of the top and the bottom. In this case, you'll notice they're both the same. 3x to the first is the highest power on top. 1x to the first is the highest power on the bottom. In that case, recall, we just cancel the x's and take the quotient of their coefficient, 3 over 1. So y equals 3 is our horizontal asymptote. And because they are the same, there won't be an oblique asymptote. You won't have both a horizontal and an oblique. There'll be one or the other, or neither. Let's go to letter B. Letter B, vertical asymptote. Oh, the denominator is 0. Our denominator is x squared minus 5x minus 14. Remember that factors into x minus 7 times x plus 2. So when I set that equal to 0, and then set each factor equal to 0, I have x minus 7 equals 0, which will give me x equals 7. And I'll set x plus 2 equal to 0, which will give me x equals negative 2. So x equals positive 7 will be one vertical asymptote, and x equals negative 2 would be a second vertical asymptote. There are two for this graph. In terms of the horizontal asymptote, you'll notice the degree is bigger than the denominator on top is bigger than that on the bottom, which tells us there is no horizontal asymptote. However, since it is one larger, x to the third, x to the second, that means we're going to have an oblique or a slant asymptote. And that's why down here, I divided x cubed plus 1 by x squared minus 5x minus 14. You'll notice when I wrote the x cubed plus 1, I had to put in the 0x squared plus 0x, because we need all the powers of x there. And when I divided, the quotient came out to be x plus 5, and the remainder, although it's not a real important thing, turns out to be 39x plus 61. And remember, that gets ignored. It's the quotient that's the key, x plus 5. Our slant asymptote would be the line y equals we've got 4x squared over x cubed minus 1. Vertical asymptote, x cubed minus 1. Set that equal to 0. We'll get x cubed is equal to 1. And that means x would be the cube root of 1. And of course, the cube root of 1 is 1. So 1 would be our vertical asymptote. X equals 1, I should say. Horizontal asymptote, well, let's see. The numerator, degree is 2, 4x squared. Denominator, degree is 3, x to the third. Remember, when the denominator has a higher power than the numerator, your x-axis, along the line, y equals 0, will always be your horizontal asymptote. The denominator's degree is bigger than the numerator, and therefore there is no oblique asymptote. Okay, hang in there. We're almost through. We're going on to letter D now. Down here, where we've got x squared plus 6x plus 5. And we're going to put that over 2x squared plus 7x plus 5. Notice they will both be factorable, but we don't have any common factors. Excuse my cat walking in here. Sorry about that. One of my cats, I should say. We have a couple. Anyway, on top we'd have x plus 2 times x plus 3, and on bottom 2x plus 5 times x plus 1. So nothing to cancel. As far as vertical asymptotes go, we'll set our denominator equal to 0. And since I factored it already, 2x plus 5 times x plus 1, I'll set each of those equal to 0. Setting 2x plus 5 equal to 0, I'll get x equals a negative 5 halves. It's one vertical asymptote. And setting x plus 1 equal to 0, I'll get x equals a negative 1. It's my other vertical asymptote. Okay. Horizontal asymptote, well, again, look at the degree, highest term power on top, and the highest power on bottom. X squared on the bottom, 2x squared, they're the same. Remember, when they're the same, you simply put them over one another, cancel the x's, and look at the coefficients, which in this case would be 1 over 2. So our horizontal asymptote is y equals 1/2. All right? And again, because here's a horizontal asymptote, there's no oblique asymptote. On to letter E. We have g of x equals 6x squared plus 7x minus 5 over 3x plus 5. Notice the numerator, 2x minus 1 times 3x plus 5 is over 3x plus 5. We can simplify this by canceling the 3x plus 5. And what we get is y equals 2x minus 1. This is just the graph of a straight line. You might recognize the line 2x minus 1. So there won't be a vertical asymptote as a straight line goes from negative to positive infinity. There won't be a horizontal asymptote as again it goes vertically from negative to positive infinity, and there's no oblique asymptote. Okay. Next we move on to letter F. And on letter F, our numerator, this is kind of tricky because there's a lot of factoring involved here. You see the difference of two squares, x to the 4th minus 16, will factor into x squared plus 4 times x squared minus 4. But then, we're not too much of a hurry, you notice that x squared minus 4 is also the difference of two squares. And that'll factor into x plus 2 times x minus 2. Okay, so our numerator basically breaks down to x squared plus 4 times x plus 2 times x minus 2. Our denominator, well, we have a common factor of x we can take out of each term. When we take an x out, we'll be left with x minus 2. You'll notice we can cancel an x minus 2 on top and bottom there, leaving me with x squared plus 4 times x plus 2 over x. Okay? Vertical asymptote. When's the denominator 0? Well, my denominator will be 0 when x is 0, because that is my denominator. simply x. So x equals 0 will be our vertical asymptote. Again, that's just another name for the y-axis. Right? Horizontal asymptote. Well, notice after we cancel my numerator, x is going to be x squared plus 4 times x plus 3, or x plus 2, I should say. The highest power term we're going to have is going to be x squared times x, which is x cubed. Okay? So when I multiply this out, I'll have x cubed plus 2x squared plus 4x plus 8. X cubed, the highest power on top, x to the first, the highest power on top. So with the numerator having a higher power, I know there's no horizontal asymptote. And because x cubed is now 1 more than x to the first, it's actually 2 more than x to the first, then I know there's no oblique asymptote. Right, Charlie? Help me out here? Okay. Anyway, well, with a little help from my cat, that wraps up this lesson. There are some extra problems that you can tackle on the website. And as always, there are some other links in the helpful links on Blackboard that you might find as well. But now you can get to work on the quiz classwork and also on the homework for this section. In the next section, we're going to be putting a lot of this to work as we actually sketch the graphs of rational functions. So a lot of this will be coming back again in the next section. And once again, I hope you're all doing well. Take care of yourself. Try not to get too stressed out. Till later. Bye-bye.